Okay, so I'm going to start with some of the topics that you should have gathered from the electricity simulation that you just played with. So being able to play with your circuits, you might have noticed that circuits must be closed in order for electricity to flow. So there must be a closed loop where the electrons will leave the battery, go through some kind of resistor, whether it be a light bulb or if you place an actual resistor, and return back. Electricity is not going to flow if you have any openings there. And in order for a light bulb to light up, the electrons need to go in through one side and out through the other. So this example here, the electrons aren't going in and out because we have an open branch right here where the electrons will go in and they have nowhere to go, so they just continue on their path. Another thing that you might have noticed is that if there's a chance for electrons to bypass something that they don't want to go through, they will. And we called it, I believe the simulation called it a jumper. I also call this an electrical short because while it's not necessarily a shortcut, be a shorter path, it's a path of least resistance. So the electrons are going to flow through. And what happens to the light bulb that gets jumped over is that not really any current will flow through it. Technically, there will be a tiny, 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 tiny amount, but essentially not enough for it to do anything. Other things that we got in words for were the terms series and parallel. So a series connection is when the resistor or the series of resistors or the light bulb, they're all on the same path. So when electrons leave the battery and make their way through, actually I'm showing you conventional current. So when the current is leaving the battery, it has to go through both of the resistors before it returns back. So the series means that they are connected in a series, in a path where the electricity has to flow through both. A parallel connection is when the resistors are connected on different paths. So the electricity leaves the battery and it can go either through the light bulb or either through the resistor. That is an example of a parallel connection. Another thing that we might have observed from the simulation is electrons don't get used up. While yes, some of their energy gets converted into light, more so heat in real light bulbs, some of their energy does get converted, the electrons are still electrons. We don't have a brighter one first and then a dimmer one second because the electrons don't get used up. That's why all the light bulbs in series have the exact same brightness. And the other thing that we noticed is that the direction of the electric current doesn't matter when lighting up a light bulb. If the electrons got used up, then you would expect that the light bulb that the electrons hit first would be the one that's brighter than the ones that get hit second. But because the electrons don't get used up, we actually get the same brightness in series. Another thing is that if there's more electrons that are flowing through a light bulb every second, if the current is greater, the light bulb is going to be brighter. So you might have noticed that in this case, when we had the parallel set up, that these two light bulbs were brighter because more electrons were flowing through. So what we're going to try to explore next is some of the rules for what causes the electrons to flow through and how we can measure them, how we can count them, how we can analyze them. So our next activity is really going to be focusing on counting the electrons. So a device that we can use to count the number of electrons to measure the current is called an ammeter. An ammeter. It will count the number of electrons that move through it. Here's the symbol whenever you might see it in a circuit. It's going to be an A with a circle around it that represents an ammeter. It is something that is counting the number of electrons and dividing the time in order to measure the current. Ammeters will measure the current in the portion of the circuit that it's placed in. So in red, we have an example of a parallel circuit here where the electrons leave the battery, go through this ammeter, and then they have the choice of choosing which light bulb they want to go through. And so the ammeter is only going to be measuring the portion of the circuit that it's in. So in this section, the ammeter is measuring 1.8 amps, more on that later, 1.8 amps through this section. We have 0.9 amps through this section, and there's nothing that's measuring the current through this middle one because there's no ammeter there. So some big ammeter no-nos is that in order for us to measure the current, we need to make sure the current goes through it. So electrons will flow through the path of least resistance and will jump around circuit elements if you allow it. And since the goal of the ammeter is to measure the current, they are designed to have no resistance because they don't want to affect the current that they are measuring. So if you ever place an ammeter in parallel to a circuit element, it will act as a jumper, a path of resistance, and see how it doesn't really go through the battery, but it is going all through, oh geez, what is that current that it's measuring at? It's all going to go through the jumper. It's going to all go through the ammeter, and that actually causes a fire typically. So make sure you always connect an ammeter in series. Another thing to know about the ammeter is that the sign of it will represent the direction. In the simulation, it's always going to spit out a positive number, but in real life, the current that it gives you represents the direction. So if it says a negative current, that means it's saying that the electrons are moving the other way. Now, just a reminder, real life ammeters measure the conventional current. So they're not measuring the flow of electrons, they're just measuring the flow of charge. So why is it called an ammeter? What is an ampere? Ammeters were invented long before electrons were discovered by some French scientist that I will not try to butcher his name, but his last name is Ampere. And he was investigating the magnetic effects of electric currents. He based it off of the current that would electroplate silver out of a silver nitrate solution at some rate for some reason. That's not really important, but they didn't really know what electrons were, so they did understand that there has to be some kind of flow of charge, and so he defined 1 amp as 6.2425 times 10 to the 18th electrons per second. So the goal of our activity that we're going to be playing with next is doing some series of experiments with ammeters. The biggest thing that I want you to focus on is that for some of the questions, you're going to investigate something, and I want you to answer it in red text with a short, clear cause and effect statement that is always going to be true. And you should be providing evidence, or you can paste in a picture for these questions. And then 7 through 11 will just be asking you to replace the red blanks like you did before. So some of the questions you might already know the answer of, but you need to make sure you're providing evidence to it. Or it asks you to make a certain circuit and it asks you to do things like that. So that's your goal for this simulation. This was a really short bit of notes, and next time we'll go over what we learned